All right, so before your broadcast of the sun, your weather forecaster, your broadcast of what's going on with the sun, we need to learn about the life cycle of a star, just for your information to be able to do this particular project, for one thing. And for another, this is how astronomy works. We need to understand what is outside just our little neighborhood. So we see stars as this great, big, beautiful thing in the sky. So if you look, you see if you get to a spot that is very dark, there's not a lot of ambient light from cities and cars and things like that, you'll see this thing called nebula. So nebula is how we see stars come to life. So we talked about the moon and how when it collided with the Earth, all this debris was shot up and it slowly formed into this sphere that we know called the moon or Luna. Uh, Nebula is all the particles that actually creates what we see with a star. So we have two different types of nebula. You have a bright nebula, which is the one that looks really pretty in the sky. It's visible. You see all this orange and yellow and purple light that doesn't seem to go with any star, and it doesn't because it's a nebula. Now, dark nebula is not close enough to see to a star to absorb the UV light. So that is the large starless region that we don't see in the sky. So bright nebula is our stars forming as they take in the UV light, and dark nebula are the parts so far away that they're not even receiving that UV radiation. So midlife, so once a nebula contracts and becomes smaller, a star starts to form. So we see this creation of a star. In the star's gravity, it had a constant odds with heat and fusion pushing it out. So during this stage, we see the protostar. So this is before our nuclear fusion is creating all of the energy that is being put out by the star. So it is trying to form, but we are not there yet. So we just see the remnants of what is beginning to happen. Gravity and fusion are not at equilibrium yet to create what we call a star. So this is our protostar. So midlife continues at about 10 million Kelvin. So because of this extreme heat, we create fusion. So fusion is the combining of atoms inside of a star. So as heat increases, the star expands, and it is pushing against its own gravity, creating an equilibrium. So that equilibrium is how we see a main sequence star start. So this means that it is coming into its adolescence. It is growing up into maturity. So most of stars remain in this for the majority of their life. So this is talking about so if you want to go compare it to the stars to humans, nebula is the forming of it to where you have a sperm and an egg coming together and starting to create a new organism. Then as it grows, it turns into infancy and turns into this proton star. As nuclear fusion continues, we see a main sequence star, which is, think of this as your working life. So this is the majority of your life that you spend working, and it is influenced by temperature at which a star burns. The hotter a star burns, the faster it runs out of fuel. So as we come to the end, we see what is called stellar death. So if we have no more nuclear fuel, if it burned too hot too fast, this stellar death is going to happen much sooner. There are several different things that can happen to this when there's no longer any fuel left. So one thing is called a red giant. So it's run out of hydrogen in its core, and so now it is burning red instead of that bright white or yellow. As the core, which is composed mostly of helium, runs out of hydrogen fuel, it begins to contract. So that means it's going to start to collapse in on itself. The contraction builds up heat and causes the outer edge of the star to expand. So even though the core is contracting, the outer edge looks like it is exploding outward. So this is what creates that red giant view. The reddish color is a cooler temperature than what it was before. So most stars spend at least some time as a red giant. After all the fuel is exhausted, it will burn out and gravity will take over from that point. So as that happens, we see the collapse of the core, and we will see the remnants. So for medium and small stars, so that would be underneath what our sun is, we see a white dwarf. So that's what will happen when it explodes to, or when it condenses into what it is at the end of its life. So white dwarfs are called, or what is called degenerate matter. That is, electrons are being pulled into the nucleus, making it extremely dense and extremely powerful gravitational pull. They are very hot due to the contraction. Some of the surface will have over 25,000 Kelvin. And remember, Kelvin is is what we use in science. And so that temperature is going to be extremely hot. Without a source of sustainable energy, they will eventually slowly cool and be doomed to be destroyed. So this will form electromagnetic radiation. So it's cooled to a point where it no longer emits visible radiation, and then it will become a black dwarf, meaning that it is no longer giving off any light. So these are theoretical and have never been observed due to the fact that they have very little or no light. So if you can't see it, you can't necessarily know if it's true or not. We just know that the white dwarf slowly puffs out because of how far away it is. Now, if it is a large star, we see what is called a supernova. So this means that a significant gravitational force pulls the outer layer of the star in at an extreme force. So that means after the star runs out of the fuel, the exterior star actually ejected into the space and blown off. So that's what a supernova is. It basically explodes outward because of how quickly it turns into a white dwarf type star. Because the white dwarf is smaller, so it takes in that energy much slower. A larger one takes in that energy way much faster, and it explodes outward because of the force that it is being pulled. So after a supernova, so when the massive star collapses, the outer portion of the star is ejected. The interior core will still remain. The interior core collapses and forces electrons to actually be into the nucleus just like this. So now we have what is called a neutron star. So instead of a white dwarf, we have a neutron star because of how large it is, because of the amount of neutrons that are actually seen in this. Due to the rapid rotation of the neutron star, after it collapses, the poles of a neutron star emit a very strange radio signal. So this is how we actually see what neutron stars sound like. So it is called a pulsar. And this creates how we know neutron stars are possible. And they are too small to be seen by telescopes, so we use the radio waves to know they exist. So one other portion of the supernova is called a black hole. So a black hole is what is left over when a supermassive star condenses at a single point in space. So it is so dense that light can't even penetrate it. So think about this. So your neutron star actually has a bright point in the center, but a black hole is so dense that you can't even have light penetrate it. It will basically destroy the light as it comes in. So in fact, that's the only way that we know black holes exist, because we look at light being swallowed by the area around it. The second method to look for it is for the event horizon. This is the point at which there is no return. But at the point the matter is heated up, sped up to the point where it emits massive X-rays and gamma rays. So we look for the X-rays and gamma rays to see if there is a black hole. So first of all, we look for the light being devoured basically by the black hole, and we look for the X-rays and gamma rays being emitted from that area too. So the combination of the two gives us our existence of a black hole. So galaxies, we live in the Milky Way galaxy. Galaxies are billions and millions or millions of stars, sometimes billions of stars that are combined into one center point. We live in the Milky Way galaxy, and on a clear night, you can see the more populated and dustier center portion of the spiral. So very clear in a very dark area, you can see the spiral much better. The first type of galaxy is an elliptical, meaning that it's a smaller one. Uh, Typically, the smallest galaxies, even though the largest galaxy in our universe is elliptical, but it looks like it has no arms. It's just a bright light. It's a very bright center with smaller ones around it. The other types are irregulars, and they're kind of off. They don't really have a shape. They look different. And then with irregulars, you have younger stars that suggest the galaxy may not have formed yet. And then there are others that are being distorted from some sort of gravitational force. So it could be a larger galaxy next to it. Could be the fact that there are many black holes or black dwarfs around it. Could be possible. Now, the spiral galaxy has two subtypes, the spiral barred and the spiral. So spiral galaxies have arms extending from their center. They're higher concentration of stars. You can see a lot more brightness from them. They actually have an easier shape to figure out. It kind of seems like it's going down the drain type thing. Almost looks like a hurricane if you see it on a Doppler radar. Spiral barred galaxies look similar to normal spiral, except they have a large bar across. So you can see as you go across this spiral galaxy, so our Milky Way galaxy is a spiral barred one. So it looks like a bar around with less arms hanging around it, almost like it's just two. And that's it for your star. Now make sure you do well on the sun newscast. There will be certain things that you have to look at and do with it, but this will help you answer some of the questions. All right.